All right, everybody, welcome back. We're talking, this is Unit 2, or Unit 1, sorry, Unit 1 on waves and oscillations. This is PowerPoint Section 4. This will be the third video, Part 4C, for the PowerPoint of Section 4. We are starting on slide 17 if you're following along in the handouts. All right, so let's start with an example. So take a moment and read this question, and we will talk about it as a group. All right. So, take a minute. Once you have a commitment to your answer, write it down. If you have a buddy, after you made a commitment to your answer, talk to your buddy. Now let's talk through this one as a class. All right. So what is tangent on this problem? Okay, if you said that the tension, T2, is going to be 1/4 of the original tension, you are correct. Okay, and if you recall back, we had things like velocity, or V, is related to the square root of the tension over the density of the string. Now, does the density of the string change at all in this case? No. Okay, the other question I think was, how is this velocity related to our wavelength? We know our wavelength, lambda, or we know V is equal to lambda F. So lambda is going to be V over F. F also stays constant, correct? Okay, so our question is, what happens to our velocity when our tension decreases? Okay, so T is going to get smaller. If T gets smaller, then V has to get smaller also. They're directly proportional to the right. So T is smaller. And if T is smaller, V is smaller. Okay, so if T is smaller and V is smaller, that means that V here is smaller, which means lambda has to also be a smaller wavelength. So we know with the decrease in tension that our wavelength cannot stay the same, and our wavelength cannot become larger. So now the question is it C or is it D? Okay, so let's go through and do this mathematically now. All right, we know that T2 is equal to 1/4 T1. So we know that V1 was equal to the square root of T1 over mu. We know that V2 is equal to the square root of T2 over mu, which is going to be equal to the square root of 1/4 T1 over mu. Okay. This will allow us to pull the 1/4 out of the square root. So we pull a 1/4 out of the square root. We're going to take the square root of the 1/4, which is 1/2, which is going to give us a 1/2 square root of T1 over mu. Now, this T1 over mu term is just V1. So I can say that V2 is equal to 1/2 V1. Everybody okay to hear? Questions, please ask. Use the chats, use the discussion board, come visit me in office hours, but please ask if you're not sure about all of these steps. Okay. Now we have this 1/2 V1. So let's apply it to our wavelength. We said lambda 1 was equal to V1 over F. Lambda 2 is going to be V2 over F, which is going to be equal to 1/2 V1 over F And this V1 over F is just lambda 1. So lambda 2 is going to be 1/2 times lambda 1. So our new wavelength is going to be 1/2 of our old wavelength. So what does that mean? It means that before, our wavelength spanned the whole thing. Now we're going to have one full wavelength in half the space. It's going to look something like this, like that, to be half the wavelength, which means we should have 1, 2, 3, 4 bumps in there, which means our answer has to be C. And if we go back to our slide, we will indeed see that our answer is C. Okay, so if we quarter our tension, we change our velocity by 1/2. Okay, so if we take our tension and we divide it by 1/4, then we have to double our frequency to have the same number of modes with the last time it's the same. This is something that you do all the time when you're tuning a stringed instrument. You tune a string instrument, you're adjusting this tension here, and by adjusting the tension, you're adjusting the wavelength. So we're going to keep, on a string, we keep the length of the string the same. It's between like 2 pins or 2 connections on your instrument, and we adjust the tension. By adjusting the tension, we're going to be able to adjust the frequency, or we're able to change the wavelengths, things like that with it. All right. So string instruments, brought up. All right, so this is going to be a fundamental frequency. Is going to be the velocity of our wave on our string, V, which we said was the square root of the tension on the string divided by mu, over 2L. So 2L is the length of the string that we have between whatever things are holding it in place on your instrument. Okay. So when you pluck it, you get a whole range of things, but only certain frequencies are resonant frequencies. They're the ones that form the nice standing waves. And so by changing our tension, we're adjusting which of those frequencies is resonance, which is how you get your instrument into tune. Okay. Now, if you look at your string instrument, maybe your guitar or your violin, you will notice you have strings of different sizes, right? Different thicknesses. Most instruments, the lengths of the strings are all pretty much the same. But you'll have some really thick strings on there. You'll have some really thin strings on there. Those different thicknesses and thinnesses have different densities. So we're changing this mu value. And by changing mu, we change our velocity, which lets us change our frequency for a given length of string. Okay, let's look at another example question. So take a moment and read this question. First thing you should figure out is, what are they asking you? All right? Common question, like, what are they asking you to find? And take a moment and write down your knowns and unknowns. So do those 2 things and then restart your video. So go ahead and pause it for a moment while I get this set up. You're gonna figure out what are they asking you to find and what do you know? Okay, welcome back. What are we asking? What are we trying to find? What's going on in this problem? We have this cute little spider who has built this web, and maybe it's between 2 wooden posts. There's a string that goes across our two wooden posts. And some bug bumps it and it starts to vibrate. And our question is, what is the lowest frequency? Now, lowest frequency corresponds to which condition? Okay, if you said the lowest frequency corresponds to the longest wavelength, you are correct. So longest wavelength. All right, so our lowest frequency is our longest wavelength. So we've got to figure out something, right? Let's go through and list our knowns and unknowns real quick. So we come along, it tells us our density is 1300, so that's mu, 1300 kilograms per meter cubed. It tells us our diameter of our string is 3.0 micrometers. It tells us it brushes along a 12 centimeter long strand, so that's going to be L, our length. And it tells us a tension, T, of 1.0 millinewtons. Alrighty. I think that's everything. And we said we are looking for the lowest frequency. So we want F1. Okay, and we said earlier that our F1, our lowest frequency, was related to 1/2L times the square root of the tension in our string divided by mu. And remember that capital T in this case is tension and not temperature or period or any of the other gazillion things we call T. So that is our tension. Okay, now we know our T, we know our L, we know our mu. Do we care about our D? Actually, we need to be really careful. This is not mu. This is actually rho. It's our volumetric one, right? We know it's volumetric because we have units here of meters cubed. We gotta find mu. That's the first thing we gotta do. So we need to find mu from rho. All right, so if we know the density of an entire volume, we're gonna wanna go to our density of our length. So mu is gonna be rho times our area. Take a moment to convince yourself of that equation. This is our cross-sectional area. And we want to know if this whole thing is mu. We want to know essentially this direction of it, but not the entire 3-dimension. So we're going to take our 3-dimensional one, which is a density per volume. We're going to multiply it by our area to give us a density per length. And we're going to make the assumption that our wire or our spider web is going to be circular in shape in cross-sectional area. So we know that the cross-sectional area A is we know our area is pi r squared, right? All right, sorry, I checked my answer. My notes didn't look quite right, but we're good. Okay, so our area is pi r squared, which means we can find our density by taking mu times pi r squared. So we're going to get rho times pi times r squared. Now the problem gave us not r, but gave us d. So we're going to take d and relate it to r. We know that d is equal to 2r, or r is equal to 1/2 d. Okay. So my suggestion is find R first, rather than trying to put in D and having to square it and make sure you don't lose factors of 2 floating around it. So this is going to give us, R is going to be 3 divided by 2, which is 1.5 micrometers. Now, how big is a micrometer? What power of 10 is that? He said 10 to the negative 6. You are correct. So that is equal to 1.5 times 10 to the negative 6 meters. So we're going to put that into mu. So we're going to have rho, which we said was 1,300 kilograms per meter cubed, times pi, times our 1.5 times 10 to the negative 6 meters squared. And when you do that and you throw it all on your calculator, you should get an answer of, go ahead and do that real quick, pause a moment, put it in your calculator. Make sure when you put it in your calculator that you have a, if you square this 10 to the negative 6, with the parentheses, and you should get 10 to the negative 9. So our question is, what are our units? Okay, we still have a kilogram divided by, now we have a meter times a meter here, so meter squared. So this is going to give us a meter squared divided by a meter cubed, which will just give us a meter. So we're gonna have a kilogram per meter, which is the correct units for mu. Okay, so now we know mu. Mu is 9.2 times 10 to the negative 9 kilograms per meter. We're getting close now. Now we have to calculate and find our F1. So F1 we said was equal to 2L, 1 over 2L times T over mu, square root of T over mu. So we're going to get 1 over 2, or L we said was 12 centimeters. We've got to convert that to meters. So this is going to be 12 times 10 to the negative 2 meters. Remember, centi means negative 2. So this is going to be 12 times 10 to the negative 2 times the square root of T over mu. T is 1.0 millinewtons. Milli is what power? You said 10 to the negative 3. You are correct. Divided by mu, 9.2 times 10 to the negative 9 kilograms per meter. Make sure when you're entering this in your calculator that you use lots and lots and lots of parentheses. Be very careful on this. It is really easy to mess this up. Your alternative is, if you have trouble getting things in your calculator, work out your powers of 10. So you have 10 to the negative 3 and 10 to the negative 9 gives you 10 to the negative 6 in the denominator. You might find you're better off reducing some of that stuff down first and then put them in your calculator. Your choice on how you want to do this. But when you do this and get everything in, you should get 43 hertz. All right. And I think we are about 20 minutes. Let's stop here and we will start another video in just a second.